Hello everyone and welcome to lecture 3. The focus of this lecture will be the divide and conquer paradigm that we briefly explained in lecture 1 when finding the worst case running time of merge sort. After looking at some examples of this type, we will study 3 methods, namely the substitution method, the recurrence tree method, and the master method to solve recurrence equations. I will then tell you the conditions under which each of these methods should be preferably used. So you should read chapter 4 of your reference book for detailed explanation and exercises. Before we begin, let us quickly recall what divide and conquer is. It is a problem-solving method that applies 3 steps in each level of its recursion. The first step, divide, divides the problem into smaller subproblems that have the same features of the original problem. In the conquer phase, if the subproblem size is still large enough, then the subproblem is further broken down recursively until the base case is achieved. Finally, in the combine phase, once we have the solutions to the smallest subproblems, we combine the solutions to eventually get the solution to the original problem. As we have seen earlier, the recursive nature of divide and conquer problems allows us to formulate the running time of these problems using recurrence equations. These equations use the function t of n to represent smaller size problems on the right-hand side. We know that this is the recurrence equation for merge sort, where the problem t of n is partitioned into 2 subproblems, each denoted by t n half and of the same size. Therefore, the base case is when the merge sort reaches a subarray of size 1. And the recursive case is when the subarray has not reached the base case yet and can still be broken down into 2 halves as shown over here. The solution to this recursive equation was shown to be theta n log n using the recurrence tree approach. The recurrence equation can have many forms. So far, in the merge sort, we have seen a trivial form in which t of n can be written as a times t of n divided by b, where a is the number of subproblems that the actual problem is divided into, and b is the size of each subproblem. But we can also have recurrence equations where the subproblems are not divided into equal parts. In this example, we see that in each recursive level, the t of n is divided into 2/3 and 1/3 of the original problem. We will learn the 3 methods used to solve recurrence equations depending on the form they have. But before that, let us look at 2 examples that are solved using divide and conquer. The first example deals with a very common problem that can be best explained using the stock market. Imagine that you work at a prestigious company, and as an employee, you are allowed to invest in the company by buying and selling only one stock of it. That means you can buy only one stock and sell it at a later date at another price. Now, why would you want to do this? Obviously, to make profit. But how do you make profit? You make profit if you buy a stock at a lower price and sell it later when the price is the highest. So, if you are given this chart for the stock price over a period of 17 days, you see that the best time to buy the stock is on day 7, where the price is $63, and the best day to sell it is day 1, where it costs $113. Well, unless you can travel back in time, it is impossible to sell the stock on day 1 before buying it on day 7. So, what would a good strategy be? In other words, what is the maximum profit that can be made using this chart? Upon careful observation, we find that buying the stock on day 7 and selling it on day 11 would yield a maximum profit of 18 plus 20 plus minus 7 plus 12, which is $43. So, one strategy that seems to work is as follows. We first find the highest and the lowest prices in the chart. Then from the highest price, we move left until we find the lowest price and take the difference between these two prices. Then in the next step, we start with the lowest price that we found and then move right till we get the highest price and compute the difference between these two prices. Then the maximum of these two differences would give us the maximum profit. But the question is, does this strategy always work for all scenarios? Let us look at a simple counterexample. According to the strategy we saw, we have to first find the highest and lowest prices in this chart. Here, the highest price is $11, which is on day 1, and the lowest price is $6, which is on day 4. So starting from the highest price, if we move to the left, we see that the lowest price is obtained on day 0, which is $10, and the difference between these two would be $1. Now, if we start with the lowest price and move to the right, well, there is no highest price to the right of this lowest price. Therefore, no profit is made, and therefore the profit would be 0. So the maximum between 1 and 0 is 1. So based on our strategy, we would make a maximum profit of $1. Looking at this graph, however, we see that if we buy the stock on day 2 and sell it on day 3, we would be able to make a profit of $3, which is higher than $1. So where did we make the mistake? The problem is that our assumption in the strategy was not correct. So the maximum profit does not always start at the lowest price or end at the highest price, as we saw in this example. With this said, we are now ready to define the maximum subarray problem. For any given sequence of positive and negative numbers, find the subsequence which gives the highest summed value of its elements. In this example, we have a sequence of 6 numbers, and we want to find a continuous subsequence that, upon adding its elements, gives us the maximum sum. The first thing that we do is we find all possible subsequence for this given sequence. Here we have 6 elements, so we would have I from 1 to 6 of I. And this summation, we all know, is equal to n times n plus 1 divided by 2. So if n is over 6 over here, we would have 6 times 7 divided by 2, which would give us 21 subsequences. Now that we have all the subsequences, next we add up the elements in each subsequence to find their sum and find the subsequence that gives us the maximum sum. In this example, the maximum subarray would be 6 minus 7 and 8, which would give us a total sum of 7. Therefore, the first strategy is what we call the brute force approach. It means that we first find all possible subarrays of a given array of length n. So if we have n elements in a given array, we have to choose 2 elements, one corresponding to the buying price and the other corresponding to the selling price. That means it would be a combination of 2 out of n, which over here would result in n times n minus 1 divided by 2. This is therefore having a running time of order O(n) square. Then we had to add up the elements of each subarray. Since the longest subarray can actually contain all the n elements, we would have to add all n elements. So we have n to the power 2 number of subarrays, and we have to add up all the elements in each of these subarrays. This therefore results in a running time of O(n) squared times O(n). Finally, after finding the sum for each subarray, we then have to compare them all to identify the maximum sum. So this would have an order of O(n) squared. So comparing these three steps, we see that the second step actually gives us the highest running time. Therefore, the running time of the brute force solution would be big O(n) cubed. Now, if we write the pseudocode for this approach, it would look something like this, where there are three nested for loops. The outer for loop actually begins or specifies the buying price of the stock. Then the second for loop determines the selling price of the stock. And inside the second for loop, we have the third for loop, which actually sums up all the elements starting from the buying price to the selling price, and therefore gives us O(n) cubed. The question is, can we do better? The answer is yes. Instead of iterating for every I and j value inside the third for loop, what we can do is actually we can bring out the definition of sum outside the second for loop and do the comparison and summation inside the for loop itself. So this would reduce to O(n) squared, which is much lesser than O(n) cubed. So returning back to the price chart given on slide number 5, we would see that the maximum subarray actually includes prices starting from day 7 to day 11, which was $43. It is interesting to note that the maximum subarray problem is challenging only when the array contains a mix of positive and negative numbers. If all the entries are non-negative, then it would not be a challenge because adding all the elements would actually give us the greatest sum. Now let's use divide and conquer to solve the maximum subarray problem. So we want to find the maximum subarray for some given array A, where low is the first element and high denotes the last element in this array. So what this approach suggests is that we divide this array A into subarrays that are of equal size. Therefore, we would have two subarrays, low to some midpoint called mid, and the second subarray from mid plus 1 to high. Now, if we take any subarray Aij within this array A, this subarray would lie in three possible places. Now let's take a look at this graph. So if this is our array starting from low to high, what we do is we divide it in half at point mid, and therefore we would get two subarrays from low to mid and from mid plus 1 to high. Now if we take any subarray Aij, Aij would either be in this half or in this half, or would be crossing the midpoint. Therefore, these are the three different places that the subarray Aij could be located. Now let's look at the third case. So at this place, as I said, the subarray Aij could be crossing the midpoint mid. This is shown by the shaded boxes. When this happens, this subarray Aij itself can be divided into two parts. One would be from I to the point mid, and the other half would be from mid plus 1 to the point j. Therefore, for the third case, starting from the point mid, if we go to the left and we find the maximum subarray, and then we go to the right, we find the maximum subarray, the sum of these two maximum subarrays would actually be the maximum subarray crossing the midpoint. Therefore, to summarize, we can say that any subarray Aij would be located in any one of those three places, and we have to find the maximum subarray in each of these three places. It is very easy to find the maximum subarray if it is in the first half or the second half. But if it's crossing the midpoint, then what we do is we move to the left and right calculating the subarrays in each case and adding them up to give us the total subarray crossing the midpoint. So we have a subarray entirely in the first half, we have a subarray entirely in the second half, and we have a maximum subarray crossing the midpoint. So by comparing these three subarrays, we could determine the maximum subarray. So finding the maximum subarray entirely in the first half or the second half of the array A is just a simple recursive technique. We would like to focus mainly on the third case, which is finding the maximum subarray that crosses the midpoint. So we have the procedure find max crossing subarray, which takes as inputs A, the index of the first element, the index of the middle element, and the index of the last element. So lines 1 to line 7 actually start from the midpoint and move to the left and finds the maximum subarray that is to the left of the midpoint. That is denoted by AI mid. Then from lines 8 to 14, we do the same thing, but we move to the right of the midpoint. And that is given by the subarray A mid plus 1 to j. So what we have to do now is just return the values of I, j, and the sum, that means the total added values of the shaded boxes. So in the worst case, we would have to go all the way from the midpoint to the very first element, which is low, and all the way from the midpoint to the very last element, which is high. Therefore, we will have to visit each and every element in the array A. If we assume that there are a total of n elements in array A, that is high minus low plus 1 is equal to n, then the find max crossing subarray function takes theta n amount of time to run. How do we know this? We can calculate this by counting the number of iterations for each for loop in the procedure find max crossing subarray. So the first for loop makes actually mid minus low plus 1 number of iterations, and second for loop makes high minus mid number of iterations. So adding these two up gives us a total of high minus low plus 1, which is basically the same as n. Therefore, we have a running time of theta n. The divide and conquer implementation of the maximum subarray problem is given in the pseudocode. Here, lines 1 and 2 check the base case scenario. That is when the size of the array reduces to just one element. In this case, it would return the index of the element and the value of that element. Therefore, the running time is some constant value theta 1. If it is a recursive case, then it would calculate mid on line 3 and then recursively call the same function with inputs mid and mid plus 1 on lines 4 and 5. Since each of these two recursive functions are half the actual size, therefore we would have a running time of t and half for both these cases. Line 6, however, considers the case where the subarray crosses the midpoint, and therefore we have A, low, midpoint, and high. So over here, we are calling the procedure find max crossing subarray, which we have studied earlier. And we know that the running time is theta n. Now line 7 checks if the maximum subarray found in the first half of A is greater than the maximum subarray found in the second half of A and also greater than the maximum subarray returned by this procedure, that means the subarray crossing the midpoint, then return the subarray that is entirely in the first half of the array A. A similar analysis is done to return the maximum subarray that lies in the second half of the array A on line 10. And finally, line 11 returns the maximum subarray if lines 8 and 10 are not satisfied. Therefore, since it is just a comparison operation, the running time would be some constant value theta 1. Now that we have dissected the pseudocode for maximum subarray problem, it's time to write the recurrence equation for that problem. We assume that n is the power of 2 and t of n denotes the running time for this procedure where the subarray is of size n. So if n is equal to 1, that is the base case, t of 1 would be some constant time theta 1. And when n is greater than 1, we would have two halves of the same problem and each having a time t of n half, which we saw earlier. Therefore, we would get to this equation where theta 1 is for calculating the base case. We had two tn halves, which was for the recursive functions. Then we had theta n, which was for the procedure related to calculating the maximum subarray crossing the midpoint. And theta 1 was a final comparison in the previous slide. So separating the base case and the recursive case would give us this equation. And we know that the solution to this equation is theta n times log n, which is same as that for merge sort. However, interestingly, there is actually a linear time algorithm that solves the maximum subarray problem, which does not use divide and conquer. I would like you to think about a solution that would take linear time to actually solve the same problem. Next, let us look at another application of divide and conquer in matrix multiplication. We all know how to multiply matrices. If A and B are square matrices of the same dimension n, then their product, denoted by C, is obtained by summing the product of each row of A with every column of B. This is done for n to the power 2 number of entries in matrix C. The pseudocode given over here actually uses three nested for loops to find the product of two square matrices A and B, and therefore it has a running time of theta n cube. Now you may ask whether there is a faster way to multiply two matrices that are square matrices, and the answer is yes. There is a method called Strasson's algorithm which actually has an order of small o n cube. That means it runs with an order which is lower than n cube, which is 2.81, which is lesser than 3. Before we get there, let us look at the divide and conquer approach to this problem. So if we assume that the dimension of the square matrix is n and is a power of 2, then we can partition each of the three matrices A, B, and C in this form, where each submatrix has a dimension n half times n half. Let us denote this equation by equation 1. Therefore, we can write the matrices in the product form as such, where each submatrix is actually the sum of the product of each row and column. For example, C11 is equal to A11 times B11 plus A12 times B21. And this is the same for the other three submatrices. Therefore, the calculation of each submatrix includes two products and one summation. Now we will use these equations to come up with a recursive formula for this algorithm. This is the pseudocode for multiplying two square matrices using the divide and conquer approach. The name of this procedure is square matrix multiply recursive, and it takes matrices A and B as input. Line 3 checks the base case. So if the matrix is of size 1, that means they have just one element, you find their scalar product and put it in C11. Since it's just a simple multiplication, it takes constant time, theta 1. If it is a recursive case, then the problem is broken down into 4 smaller problems. As we saw earlier, each submatrix includes 2 multiplications and 1 addition operation. These can be seen in line 6, 7, 8, and 9, which is actually calculating the submatrices C11, C12, C21, and C22 using the same procedure that we saw in the slide before. Therefore, the multiplication operations can be done in a recursive manner by calling the same function on the submatrices and then adding them up using the addition operation. Since each recursive operation has a size of n half. Therefore, we would have two n halves for each subarray and summation that is of the order n square for calculating each subarray. So therefore, there are 8 recursive calls to this function, where each recursive call actually contributes t(n half to the running time of this whole procedure. So the recurrence equation for matrix multiplication using divide and conquer can be summarized over here. The base case takes some constant time θ1, that means when n is equal to 1. And when we have the recursive case, we would have 8 recursive calls, and therefore we would have a total of 8 times t(n half contribution to the running time. And the addition takes θn square amount of time. So putting all of them together, we would have this equation where θ1 is actually finding the midpoint of n. 8 times tn half are the 8 recursive calls, and θn square is the addition to calculate each sub-matrix. Now, given this recurrence equation, later on using master method, we will show you that the solution is g of n is equal to theta n cube. So it is not faster than the naive method that we had shown you in approach 1. So the key to Strassen's method is actually to try to reduce the number of multiplications from 8 to 7. It replaces one of the multiplication operations by a number of addition operations, and therefore it reduces the order of running time from n cubed to something lower than n cubed, which we saw was n to the power 2.81. So the third approach is using Strassen's method, which has 4 steps. In the first step, we divide the input matrices A and B and the output matrix C into n half submatrices, similar to what we had done in equation 1. Doing so just takes a constant time θ1 because finding the midpoint of n is very straightforward. In step 2, we then create 10 new matrices S1 to S10, and the size of each matrix is also n half times n half. And these matrices are obtained by sum or difference of two matrices that we created in step 1. So we can create all the 10 matrices in time θn square. In step 3, we use the submatrices that we obtained in step 1 and the submatrices that we computed in step 2, and we create 7 new matrices. And these matrices are actually the products P1, P2, and P7, and they have the dimension n half. In the final step, we can compute each of the output submatrix C11, C12, C21, and C22 by adding and subtracting various combinations of the product matrices P1 to P7 in step 3. And all of this can be done in θn square amount of time. So we will see that the recurrence equation for Strassen's algorithm would actually be 7t(n half plus θn square for the recurrence case. In step 1, we divide our matrices using equation 1. Then in step 2, we use those submatrices to actually calculate S1 to S10. And these include addition or subtraction operations. And since we have 10 addition and subtraction operations, this would have a running time of θn square. After calculating S1 to S10 matrices in step 2, we then calculate the product matrices P1 to P7 in step 3, where P1 to P7 are actually multiplication operations of two submatrices of the dimension n half. Pay attention that in step 3, while calculating product matrices P1 to P7, we actually have 7 multiplication operations, which unlike the previous approach, it has one multiplication operation lesser. Finally, in step 4, we calculate the output submatrices C11, C12, C21, and C22 by adding and subtracting the product matrices that we obtained in step 3. Since this is addition and subtraction, we have seen that the running time for such operations is θn square. Therefore, as n grows asymptotically large, we can say that the Strassen's method would outperform the square matrix multiply procedure as it replaces one of the multiplication operations with addition and subtraction. As an exercise, I would like you to try to work out this multiplication using Strassen's algorithm. This slide summarizes the three approaches that we have studied for matrix multiplication, where we see that the third approach, Strassen's algorithm, actually has the better running time of big O n log base 2 7. And this algorithm is very useful, especially in parallel computing. So far, we have seen how to use divide and conquer to solve two actual problems. Let us now learn how to find the solution to recurrence equations for these problems. The first method is the substitution method, which involves two steps. First, we have to guess the solution, and then we use mathematical induction to find the constants and prove that this solution actually works for the recurrence equation. Keep in mind that the substitution method helps us establish only the upper or lower bounds on the recurrence equations. So to summarize, we first have to prove that the solution holds for the base case, which is n is equal to 0 or n is equal to 1. And then in the inductive step, we have to show that if it is true for n number of inputs, then the solution is also true for n plus 1 number of inputs. Now let us look at an example where we want to find the upper bound for a recurrence equation, which is given over here. So the first thing that we do is we guess a solution. And my guess is big O n log n. So this tells me that there exists a function t of n that belongs to the set big O of n times log n. So based on the definition of big O notation, I can write that this function t of n is less than equal to some constant c times n log n. We now have to prove that this solution actually holds for the base case as well as the recursive case. For now, let us focus on the inductive step. So in the inductive step, we have to prove that this bound holds for all positive values m, which is less than n. Now, what would be the best choice for m? If we look at this equation, we would see that we have floor n half over here, which obviously is lesser than n. So if we set m is equal to floor of n half and substituting this in this equation, we would get this. So if we number this equation as equation 1 and this equation as equation 2 and substituting equation 2 in equation 1 for the t n half, we would get this. To further simplify our analysis, we know that there exists a relationship floor of x is always less than equal to x. So using this property, we can actually show that this is greater equal to this by removing the floor operator. Further expanding this would give us this equation, and therefore we know that log base 2 of 2 is equal to 1, so this simplifies to Cn plus n. In the final step, we have to make sure that T of n is less than equal to Cn log n, as we had proposed earlier in our solution. Therefore, this term should be equal to 0. So we can write this expression as n times c minus 1. So we know that for all values of c that are greater equal to 1, this term would go away and we would get this inequality. Now that we have shown the inductive hypothesis, what remains in the mathematical induction is to show that the solution also holds for the boundary conditions. So this is the base case. The good thing is that for the base case, we can choose n naught to be any value such that it satisfies this condition. So if we put n is equal to 2 in the equation, we would get t of 2 is less than equal to 2c. Let's call this equation number 3. And if we put 2 in equation number 1 that we saw in the previous slide, it would reduce to this, where t of 1 is some constant time, which we consider 1. So from equation 3 and equation 4, we see that t of 2, which is equal to 4, can be plugged in over here, and we get some c value which is greater than equal to 2. Therefore, we can say that for n not equal to 2, we have some positive c value greater or equal to 2 for which this solution actually is true. We saw that solving the recurrence equation using substitution method is quite straightforward. But the only challenge is, how do we get a good guess for the solution? Is there any trick? The answer is no. The only way to come up with a good guess is through experience and actually by looking at the structure of the recurrence equations. So if you see a recurrence equation similar to a recurrence equation to which you already know the solution to, then you can make a good guess by using the same solution as your beginning guess. For example, if you look at this recurrence equation, we see that it is very similar to what we just worked out, but it has an additional term 17 in here, which makes it look a bit difficult. But we know that as the function or as the value of n grows sufficiently large in a asymptotic manner, then the difference between n half and n half plus 17 would not be very large. And therefore, it would be a good guess if we take t of n to be big O of n log n. Another way to make a good guess is to prove the upper bound and the lower bounds for a given recurrence equation and then reduce the gap of uncertainty between these bounds. That means we try to bring the upper and lower bounds closer to each other, and we reach a point where these two would actually meet. For example, in this equation, we see that if we take the lower bound to be omega n, which is true, as we know that the solution to this is n log n, and we take the upper bound to be big O of n squared. So these would also be solutions to this recurrence equation, but they are loose bounds. So in order to tighten the bounds, what we do is then we could increase this by n log n, and we could decrease this by n log n, which would again be the same solutions and would give us actually a tighter bound, which is theta n log n. Sometimes it may also occur that you make the right guess for a given recurrence equation, but when you work out the math, you do not actually get what you expect. As an example, take a look at this recurrence equation. So we guess that the solution to this equation is t of n is equal to big O of n. And we try to show that this is less than equal to some constant c times n based on the definition of big O. Now, when we substitute m is equal to n half for some m value less than n, as we did in the very first example under substitution method, we would arrive at this equation, which when you factorize the c, you would get the sum of n half plus n half, which would be cn plus 1. Over here, we notice that we have an extra term. And we cannot remove this term because there is no subtraction. There is an addition operation. So the solution is not the same as we expected. Now, how do we solve this problem? Should we make a larger guess, maybe big O of n square? Actually, no, because big O of n is the right solution to this problem. What we should do instead is we should make a stronger inductive hypothesis. What I mean by a stronger inductive hypothesis is that we should be able to modify this Cn solution in such a way that when we arrive at this part, we would have a subtraction term on the right-hand side, which would then allow us to actually prove the correctness of the solution. Therefore, in the example that we just saw, all we have to do is we have to subtract a lower order term on the right-hand side of the solution that we guessed for the problem. So instead of just writing C of n, I would write C of n minus d for some d value which is non-negative. Now, when we plug in this solution for m is equal to n half, as we did earlier, we would have a minus d term added in our derivation, which reduces to cn minus 2d plus 1. Now we have to remove the same form as we guessed initially. So we should remove Cn minus d from this entire term. So removing d would leave us with Cn minus d plus 1. And then I would have Cn minus d, and this would be my remaining term. So we keep Cn minus d, and we have to find the condition under which this remaining term would actually become 0. And the condition is when d is greater than or equal to 1. Therefore, we should be very careful when trying to obtain the exact form of the inductive hypothesis. For example, in our previous recurrence equation, which is given over here, if we guess that the solution is C of n instead of C of n log n, and we work out the math and we arrive at this expression, we cannot say that this is exactly the same as what we were expecting, because it takes a form which is different from our initial solution. Over here, we do not have a plus n. So this would not be correct, and therefore such a conclusion would be wrong. Sometimes it may happen that we come across some recurrence equations that are less common. For example, look at this equation where we have a log n and we have a square root of n. Well, this should not scare you because this can be easily solved by using the technique called change of variables. So what we have to do is we have to find some m value which is defined as log m, and we know that 2 to the power m is equal to n, and by substituting that in this equation it would change to t of 2 to the power m is equal to 2 times t 2 to the power m half plus m. Now we can further simplify this by replacing the term t 2 to the power m with the new term s of m. Doing so would give us this equation. So this is something that we are all familiar with, and we know that the solution to recurrence equations of this form is actually O of m log m. Now what we have to do is we have to change back the S of m notation to T of n. Doing so, we would arrive here, and we know that m is equal to log of n, and replacing it, we would actually get this. Therefore, the final solution to this recurrence equation would be as shown over here. The next method that we will be studying is the recursion tree. We have seen the recursion tree in solving the merge sort earlier. In the recursion tree, we know that each node in the tree actually represents the cost of a single subproblem. So what we do is we add up the costs along each level. That would give us a level-based cost. And to calculate the total cost of the tree, we would add up the cost of all levels. So when do we use a recursion tree? Generally, the recursion tree method is used when we want to generate a good guess, and then we validate our guess using the substitution method. For example, let us assume that we are given this recurrence equation and we want to use the recursion tree to come up with a solution for this equation. We know that we can choose the value of n in such a way that the floor or ceiling operators would actually not impact our solution. So for now, let us assume that we remove the floor operator. In other words, we assume that n is a power of 4, and therefore the size of all the subproblems would be some integer value. Drawing the tree for the recurrence equation would look as such. Initially, we have t of n. When we divide it into smaller parts, we would have cn square, which reduces in size by a factor of 4 in each level. So when you take it one level further, you would have n divided by 4 to the power 2. So if we denote this as level 0, this as level 1, and this as level 2, we see that in level 0, the size of the subproblem is n divided by 4 to the power 0, which is equal to n, which is correct. Then in level 1, the size of the subproblem becomes n divided by 4 to the power 1, which is n divided by 4. And we see that is right as well. In the second level, it would reduce to n divided by 4 to the power 2. Therefore, in general, we can say for every level I, the size of the problem becomes n divided by 4 to the power I. Therefore, the last level in the tree would be the level that contains the leaves. That means it would have problem sizes of 1. Or equivalently, we would have n divided by 4 to the power I is equal to 1, which becomes I is equal to log base 4 times n. So over here, we see the complete tree up till all the leaves, which is shown over here. We know that the last level is log base 4 of n, which we calculated earlier. Now let's try to calculate the number of nodes in each level. We see that in level 0, we have 1 node. In level 1, we have 3 nodes. In level 2, we have 9 nodes. And therefore, to generalize this, I can say that in level I would have 3 to the power I number of nodes. Therefore, in the last level, which is log base 4n, I would have 3 to the power log base 4n number of nodes, which is equivalent to writing n to the power log base 4 of 3 as per the properties of logarithm. Therefore, in the last level, I have n to the power log base 4, 3 number of nodes. Since we know that the time taken to solve the base case, that means the nodes which are of size 1, is some constant time t of 1. Therefore, what we have is the cost for calculating all the n leaves would be n to the power log base 4 3 times theta of 1, which would be equivalent to writing theta of n to the power log base 4 3. So now that we have the costs along each level, all we have to do is we have to add up these costs for all the levels. And that is given over here. So by adding them up, we would get this equation. This is a familiar equation, and you should be knowing that this is actually what we call the geometric series. So if you have 1 plus x squared up to xn, you can reduce it to as such. Solving the equation, we see that we arrive at this simpler equation where we have a term with order n squared and another term with theta of n to the power log base 4 3. As we are interested in the asymptotic behavior of this function, when n grows large, this would become insignificant, and therefore the order of the time would be of O n squared. So we can say that this would be a good guess for the recurrence equation. And using this guess, we can actually prove or verify the solution using substitution method. Now we want to show that this is the solution to the recurrence equation. So we say that t of n is less than or equal to some constant d times n squared, where d is positive. So using the same constant c as we have used earlier, we can write this equation, and then by doing the derivation, we would arrive at this point. So this is very important. So this step tells us that this solution would satisfy the recurrence equation for values of d that are greater than or equal to 16 divided by 13 times c. And how do you get this? This is how you do it. We can divide this expression actually as this. That means 1 times d times n squared minus 13 divided by 16 times d times n squared plus cn squared. So we know that the difference of this two was actually 3 divided by 16. So doing so allows us to remove the n squared and to factor the remaining term. So from this remaining term, which should be actually greater than or equal to 0, we see that the condition is d should be greater or equal to 16 divided by 13 times c. Now, as an example, try to construct a recurrence tree for this given equation. In this example, we see that the problem is not divided into subproblems of the same size, but rather each subproblem reduces in size at a different rate. The tree for this recurrence equation is seen over here. So the node at the top, which is called the root, branches out into two parts, where the left part actually reduces by 1/3 of the original size, and the right branch actually reduces by 2/3 of the original size. This partitioning continues until we reach leaves of size 1. But we note that these two branches do not grow at the same rate. That means one side of the tree grows at a faster rate while the other side grows at a slower rate. So the longest simple path from the root to the leaves would be this path. Looking carefully, we see that the size of the problem at level 0 is 2/3 to the power 0, which is n. So we have the same over here. Similarly, at level 1, the size of each subproblem becomes 2/3 to the power 1, which is 2/3 times n, which we have over here. Similarly, we keep doing this until we reach the level where there is only a subproblem of size 1. Therefore, at the kth level, we would have a subproblem of size 1, and therefore we get this relation. So this can be further simplified to this. The total cost can be calculated by multiplying the cost of each level to the number of levels in the tree. That is O of Cn log base 3 to n, which is equal to big O of n log n. In a complete binary tree, where the subproblems at each level have the same size, we would have exactly n to the power log base 3 to 2 leaves. But in this case, since the binary tree is not complete and balanced, we would have fewer leaves than that of the complete tree. We relax the calculation of the cost here to facilitate our analysis. Or as they say, we tolerate the sloppiness in the calculation of the cost and go with big O n log n as our guess for the solution of this recurrence equation. Now that we have guessed our solution, next we have to use substitution method to verify that this solution actually is the solution for the recurrence equation. So we define T of n as less than equal to d times n log n, where d is a constant value, and then we plug it in the equation, and we reach this point after the mathematical manipulation. And over here we see we have a negative term and a positive term. So together, this should be greater than equal to 0 for this expression to hold. So the condition under which these two terms would be greater than equal to 0 is when d is greater than c divided by log 3 minus 2/3. The last method to solving a recurrence equation is the master method. Among the three methods, this is the most fastest method, but the drawback is that it can be applied only on equations of this form. Also, to use it, you will have to memorize three cases. So the recurrence equation of this form actually describes the running time of an algorithm that divides the problem into a number of subproblems, and each subproblem is of size b. Therefore, if you remember the merge sort, a was equal to b was equal to 2. In the Strasson's algorithm, a was 7 and b was 2. F of n over here actually denotes the cost of dividing the problem into smaller problems and combining the solutions to the subproblems to get the actual solution. The master method is defined as follows. If a and b are greater than 1 and Tn is a recursive function of the form given here, then the function f of n determines the asymptotic bound of Tn depending on which of these three conditions it satisfies. So when applying the master method, you should make sure that your recurrence equation is of this form, and you should learn these three conditions by heart. We see that in all three conditions, the function f of n is compared with n to the power log base ba. So the larger of these two functions would actually determine the solution to that recurrence equation. So as in case 1, if the function n to the power log base ba is larger than f of n, then the solution is guaranteed to be theta of n to the power log base ba. In case 3, if the function f is larger, then the solution would be theta of f of n, which is very easy. In case 2, if both the functions are of the same size, then what we do is we multiply a logarithmic factor and we get a solution of theta n to the power log base ba times log of n, which would be equal to theta of f of n times log of n. Note that the solutions are given in the form of theta notation. This means that it is a strict bound and is bounded from above and below by this function. So in the previous case, we saw that we were getting solutions in terms of big O or big omega. But in master method, the guaranteed solution is in terms of theta. Now let us try to solve this recurrence equation using the master method. We see that A is 9, B is 3, and f of n is n. So when we plug in B and A in this equation, we would get n to the power log base 3n, which is equal to n squared. So f of n, which is n, would belong to the set big O times n log base 3n minus epsilon, where this epsilon should be some positive value greater than 0. So if we take epsilon to be 1, this would be n to the power log base 38, which again is higher than n to the power 1, which would be the order for f of n as we see over here. So since this condition is satisfied, we can apply case 1 of master method, and we can directly say that the solution to this equation would be theta n squared. Now let's take a look at another example. Over here, we have a is equal to 1 and we have b is equal to 3 divided by 2. F of n is also 1. So if we plug in a and b into this equation, we would get this, and we know that the value for this exponent part would be 0. So n to the power 0 would be equal to 1. So we see that f of n is equal to n to the power log base ba. So both are equal to 1. So this would be case 2 of master method, and since they are equal, we would multiply the logarithmic factor and we would get t of n would be the solution of theta of n to the power log base ba, which was equal to 1, times log of n, which would be equal to theta log n. We now see how to apply case 3 in example 3. Take a look at this equation. A is equal to 3, B is equal to 4, and f of n is n log n. Plugging them in n to the power log base ba would give us this, which is of the order n to the power 0.793. Next, we should find some epsilon value such that f of n would be bounded from below by this. So if we take epsilon to be something approximately close to 0.2, adding 0.2 to this would give us 4. So we would have n to the power log base 4 times 4, which would be n to the power 1, which is equal to n. And we know that f of n belongs to the set omega n. So we have proved one part of case 3. The second part is to show the regularity condition also holds for n. So what is the regularity condition? This is the regularity condition. It says that for sufficiently large values of n, there should exist some c value that is less than 1 such that this condition would hold. Now, by plugging the values for a and b over here, we can see that the c that we can obtain would be 3/4 that would satisfy this condition. So we rely on case 3 and we say that the case 3 actually is satisfied and the solution is thus theta of n log n. Now let's take a look at this final example. Over here we see that we have an equation which is of the form that can be solved using master method. Over here a is 2, b is 2, and f of n is n log n. So when we plug in the values of a and b into n to the power log base ba, we would get n. If we follow the master rule, we see that this could be satisfied using case 3. But is it actually the case? The problem over here is that the problem that we have is not polynomially larger. That means the ratio of f of n, which is n log n, to n to the power log base ba is log of n, which is logarithmic and not polynomial. So we expect this ratio to be of the form n to the power some epsilon, which is positive, and not some logarithmic function. If this is the case, then we could solve using case 3. If not, then we cannot use the master method, and we probably have to use the recurrence tree approach.